Hey, everybody. So we're going to talk about a new concept today. We're going to talk about two big things, a discrete random variable and a probability distribution function. So let's jump right to it, and we're going to start with the idea of a random variable. Right? This is a very good example of a couple of words we're putting together that have meaning in common language. They have meaning in other places in math that are not going to be exactly the same as how we use them in statistics. So there's a very technical definition of random variable, but for our purposes, we're going to think of it this way. It is a variable whose numeric value is determined by the outcome of a probability experiment. It's going to give us a very powerful notation. This is also going to be, you may have experienced this before in mathematics. This is going to be something that seems at first to overcomplicate a relatively simple idea. We are not doing this because we just want to make things more complicated. The notion of a random variable is going to be very helpful in the future. However, we're going to learn about it on examples where it's not very helpful, right? If you were to multiply 12 times 2, I think most of us might do that in our heads, right? But you might use it as an example when you're teaching somebody how to multiply numbers using that old algorithm where you write it down like this, right? And you can go through all the steps. So it's a simple example that it's not what you would really use to do this problem, but you learn it so when you need to do more complicated things, you can do it. This is how random variable is going to feel. So let's try to see exactly what I mean by this. Let's go back to our old experiment. Flipping a coin 3 times. Right. We have seen this sample space for this experiment numerous times already. Heads, 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 tails, heads, tails, heads, tails, heads, heads, and so on. It's always nice to have it written out. Okay. So remember what I said, a random variable is a variable whose numeric value is determined by the outcome of a probability experiment. And here's our experiment. Here's a random variable. I might name the random variable x is equal to, and then I'm going to have an idea here, a thing that can be counted or measured. In this case, it's going to be the number of heads flipped in 3 attempts. Right? So we name this random variable, and if I flipped my coin, it would have a numeric value. If I did this experiment and got 1 head, then the value of x is 1, right? So it's a variable whose numeric value is determined by the outcome of an experiment, right? In this case, right, for this particular experiment, x can take on the values 0, 1, 2, or 3, right? That's all the possibilities for x in this experiment. No heads, 1 head, 2 heads, or all 3 heads, okay? So we'll use these random variables. One of the things we're going to do with them is we can use them to name events, okay? So for instance, previously I might have done something, well, let's first, generally we write something like this. We write P of an event is equal to, and then we'll get a probability of that event, right? Some number. That's our general form. The pieces are always in place in these places. And so in the past, we may have said something like, how about A is equal to flip 2 heads? and then I do the probability of that event, and I go to my sample space and I see these 3 are all the outcomes with 2 heads out of 8, and so I get 3/8, right? Well, we're going to do the exact same problem. All I'm going to do is change the notation and use this new random variable. And instead of writing A, I can name my event using X. Look at what X is, the number of heads flipped in 3 attempts. So if I write, what's the probability that X equals 2? What does this statement, X equals 2, means? Well, that means I'm going to substitute in my head, I'm substituting in my head X with this phrase. The number of heads flipped in 3 attempts is 2, right? So now I've written this event, flipping 2 heads, using the notation of the random variable, right? And the answer is, of course, the same, okay? This looks very strange, right? This is probably very new to all of us, that we've got this equal sign inside something, and it's part of an equation, and there's an equal sign in the equation. All we need to remember is everything in this parentheses is naming an event. And how are we naming this event? Is by using our random variable. So X equals 2, this is the event. And now I'm just quoting what I wrote over here. The number of heads flipped in 3 attempts. Right, that's what it says there. And then our equal sign is just is 2, right? And it becomes very simple. Okay, so this is something I want us to really make part of our habit, part of our practice when we write these things. Have I written down the right event? Okay. Now, like I said a moment ago, this seems worse than doing this, right? Why did we go through all this extra effort and when we already had this nice method, okay? Most of the answer to that question is going to come in a couple of sections, a little further along in these videos, right? Because we've got to get to the part where this notation is useful. However, there is one little example I can give here that's kind of nice. Suppose I now was interested in writing a question about flipping 3 heads. I don't have to name a whole new variable. I can just write, what's the probability that X equals 3? This is asking the probability that the number of heads flipped out of 3 attempts is 3. That, of course, is 1 out of 8. I can do the same thing for X equals 1. What's the probability of flipping 1 head? That, again, is 3 out of 8. And I could ask the probability of flipping no heads, which is, of course, flipping 3 tails. And that's also 1 out of 8, right? So I've now, by naming this event, or naming this variable, this random variable in a general way, I can now name all these specific events without having to go through and name, write specific statements for each of these. Okay, so this is just the tip of the iceberg of this notation being useful to us, but it's not a bad one. This makes things nice and easy. And you can imagine if instead of asking flipping a coin 3 times, if I was asking about flipping it 30 times, this is much more flexible than having to use, right? We'd run out of letters and we'd have to come up with some other symbols to use for naming the events of all the different kinds of numbers of heads we could flip in 30 attempts. Okay, so let's move forward a little bit. When we have these random variables, one thing we will do with them is organize information about them. In particular, we're going to spend some time building what we call probability distribution functions. I'm putting functions in parentheses because I will often say probability distribution when I mean a probability distribution function. Lots of textbooks will do that as well. But this is what we mean. They are functions. Sometimes we'll call it a PDF as well. So what this is a table or a formula that gives the probability for every value of a random variable, well, I'll just say of a random variable. Right? In other words, using that random variable, if you go through all the values it has, right? In our case, we just had x had the 4 values 0, 1, 2, or 3. Each of those values, remember, represented some event. We give the probability of all of those events, and that's our probability distribution function. Sometimes it's a table, and that's actually most of what we're going to do. That's all of what we're going to do for a little while is tables where we can write down all the values. Eventually, we'll get to functions when you have a probability, when you have a variable that has, let's say, several hundred possible values. You don't want to spend time writing them all down, but you might have a formula that if you simply plug in something simple to it, you can compute it very easily. So it's in essence given, and we'll see examples of those a little ways down the road. So we've got the information to build a probability distribution function for the variable x, right? So we've got this random variable x, the number of heads flipped. I'll just keep the same notation in 3 attempts. Sorry, I had a thought there for a minute, and then I thought better of it. One way we can organize this PDF is in a table, and this is a typical way this table might look. We write x, p of, there's different ways to write this side. I'm going to write it this way, and I'll explain what that means in just 1 second. Sometimes people write a little x over here. In any event, in this left column, I'm going to write 0, 1, 2, and 3. These are all the possible values of x. And right next to it, I'm writing p of x equals this little value of x, right? So we often let the big X represent kind of the general concept and the little one represent the specific value. So the thing that goes here is the probability that x equals 0, right? I don't usually write this out. I just want to make sure we're clear what I'm writing here. This is the number equal to the probability that x equals 0. We already figured this out over here. This is going to be 1/8. Let's do it in decimals just to shake things up. The next place, we're doing the probability that x equals 1. And we said that that was 3/8, 0.375. Same thing for 2, and then we're back to 1/8 here, right? And again, all we would usually write is these, but to make it clear, each of these values in the left-hand column, the right-hand column, is the probability of x equaling the value in the right-hand column, okay? And so this thing here is our probability distribution function. Okay? It gives us the probability for every value of the random variable. Okay? So of course, again, this is one we already had with a pretty simple picture right here. But as we'll see when we get to more complicated problems, it's nice when there's more than these 4 options, and being able to build these things or having these things available to us is quite nice, right? When things get a lot bigger. Okay, so one more time I will note values of the variable here, probabilities of the variable equaling that value here. In other words, the probabilities of the corresponding events. Okay. Ooh, that looks like an 8. That is a 5 right here. Okay. Now, something else to notice. First of all, like all probabilities, every value here should be between 0 and 1, right? This is just something we've already said before. In this new notation, the probability of each outcome, or the probability of x being each value it can take on, has got to be between 0 and 1, because they're probabilities, and probabilities are always between 0 and 1. So there's nothing new there. The other thing to notice is that if we add these 3 up, so if you sum these, 4 numbers up, you'll see that they add up exactly to 1. And this is not an accident, right? And we can write this statement using this fancy notation. This is our Greek letter sigma, remember? And we write, it's just a way of saying sum up all of these things, okay? That's the symbol you can think of as saying sum up all of the things like this. So for us, that means adding up all of these is always going to add up to 1. Okay? The sum of all these probabilities is going to be 1, right? Why is that? Well, one way to think about it is these are all the possible things that could happen, right? So if I could ask a question like, what's the probability that x equals 0 or 1 or 2 or 3, right? Remember when we use our or statements, that's our addition rule. These are always going to be mutually exclusive events because x can't be 0 and be 1. It's going to be one or the other. So we simply add all them up. And if you're adding up all the possible things that can happen, if you're talking about an or statement of where all the things that could happen, one of them is going to happen. So it has to be certain, meaning probability 1. Okay. A little tiny asterisk next to that. When we get into more complicated problems and the computations of these get a little uglier, we might find ourselves with long decimals that we're rounding. And once in a while, because of rounding, if you actually add up what you've written, you might get something like 0.99 or 0.98 or 1.01. It doesn't automatically mean you're wrong. It just means because you're rounding, it could, it gets off. Rounding is introducing error, right? When you round, you're just saying, I accept a certain amount of error in this problem. And that's fine. If I've asked you to round it so it doesn't quite add to 1, that's okay. If it's off by a lot, you should rethink what you've done, right? Rounding errors are not going to be off by more than, a tenth maybe or a hundredth, depending on how much we've been rounding. Sorry, not a tenth, hundredth, or maybe a hundredth or 200th, something like that. It would never be 0.9. That would be way too big of an error. Okay. Let's see. So I'll just reiterate, these 2 facts are always true. They're always, 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 always true with that little asterisk for the rounding errors. So when you're working on exams and quizzes or your homework or projects, or even better, doing statistics in the real world, if you find yourself with a probability that's not between 0 and 1, or if you find yourself with a probability function and you add these up and they're not 1, something's wrong that needs to be fixed, okay? All right, let's do another example. Let's try a slightly different experiment. My experiment now is going to be rolling 2 4-sided die and add the result. So the result of our experiment is the number that the 2 dice sum to. I roll these 2 dice, I get a 2 and a 4, I add them together, I get 6. That's the result, okay? I want to create a PDF for this experiment, a probability distribution function, which means I need to create first a random variable. So I'm going to create the random variable s equals the sum of, how can I say, I guess I'll just say rolling 2 4-sided die, right? I'm going to assume they're fair die. They have the numbers 1 through 4. Each number is equally likely on each die, okay? So there's my random variable. I want to create a PDF, which means I need to create, I need to find the probabilities for each value of s, okay? So let's attack this one with drawing out the sample space again. We'll do some without that. I want to kind of wean us off of writing out sample spaces, but I think it's still pretty useful to look at them. So I'm going to create the sample space this way. I'm going to write so what I'm doing is I have a column on the left and a column along the top that represents each value that each die could roll. So the column on the left is one of the die, the column on the right is the other die, and we can represent all the possible rolls this way. Let me make this easier to look at, maybe a colored line to separate these, because the grid in the middle now is going to be our sample space. And all I'm going to do is this square, for instance, is what happens if you roll a 1 and a 1. We get a 2. If I roll a 2 and a 1, I get a 3 and a 1, a 4 and a 1, and 5, and so on. So each square in here is telling you what is the sum of rolling from the number from the left column and the number from the top row. Okay, so I'll just fill this out. We get 3, 4, 5, 4, 5, 6, 5, 6, 7, 6, 7, 8. Okay, and so now this part in the middle, not the middle, this part, the lower right hand 16 squares here represent the sample space, and further, each of these is equally likely to happen because all of these are equally likely to happen. So these are all the possible combinations in the same with the same likelihoods. Okay, so this will let us quickly make our probability distribution function for this random variable. So what can we do? Well, I'm going to write the table S P of S equals S. Down this column, I write every possible value. So what are all the possible sums? I can sum to 2, to 3, 4, 5, 6, 7, and 8. And then next to it, I'm just going to write the probability of each. And I'm just going to get this from counting. There are 16 total options in this square. There's only one of them that's a 2. 2 of them are 3s, 3 of them are 4s, 4 of them are 5s, 3 of them are 6, there are 2 7s, and 1 8. And so we see the probability distribution for this random variable S, right? Notice all of these are between 0 and 1. They're all positive, but they're all a fraction smaller than 1. The numerator is always smaller. If you add these up, 1 plus 2 is 3, 6, 10, 13, 15, 16 16ths. They certainly sum up to 1. Okay, so this is another probability distribution for this random variable. Okay, so these are our first introductions to random variables and probability distribution functions. We'll stick with tables for the moment. I want to also mention I'm only dealing right now with discrete random variables, right? Just meaning that the variables can only take on discrete values, right? If you remember discrete versus continuous from earlier videos, there are only particular values you can take on here. Later, we'll get into continuous random variables, things like maybe there is going to be a birth and I could have the random variable, the birth weight of the baby. And that's a continuous variable, right? Weights are continuous. Things that we measure are usually continuous, and we'll have to deal with those a little bit differently. We certainly can't write out every single possible birth weight because there's an infinite number of possible birth weights. And when we have those, we'll have continuous probability distribution functions as opposed to discrete distribution functions. Those will almost always come in the form of functions, equations, or formulas, though we'll have tables that will approximate them that we'll use. But we'll get into all that later. That is it for this one. Thanks, everybody. I will see you next time.